Good morning and welcome to day 2 of Black Hat 2015. We've got a few announcements for you. Stop by the business hall located in Shoreline A for sponsored sessions in Theater A and B. Be sure to check out all the Black Hat Arsenal and Breakers D, E, J, K. Sponsored workshops are in Mandalay J, K, and L. You are in Lagoon K for the session name Web Timing Attacks Made Practical with Tim Morgan and Jason Morgan. I also would remind you to put your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick it up. So, good morning. We're glad you're here, and let's introduce welcome our speakers.
Thank you. Thanks for coming. I'm Tim. This is my brother Jason, and we want to explain to you what we researched in the area of web timing attacks. So, what are timing attacks? Well, just about any piece of software has situations where it needs to do some kind of security critical operation. Things like authentication, authorization checks, or cryptography. And sometimes in those situations, it's really important that the application may return the result of that operation, whether success or failure, to the user or to or a potential attacker. But it's really critical that the details of how the decision was made are not exposed. So in a really trivial example, consider a web application that you're trying to log into, and if you type your username and you mistype your password, if the application comes back and says, oh, the password's wrong, you messed up character 3. You know, that's kind of absurd, but if it were to do that, then clearly you could guess the password one character at a time, right? So in those situations, we have to be sure that that information doesn't leak, and depending on the operation, what information is critical just varies. With timing attacks, what we can do sometimes is if we can measure the execution time of those critical operations, then we can actually learn information about the inner workings of how the decision was made. So that kind of information can leak, and therefore it can expose vulnerabilities. So there's been plenty of research in the past in the area of cryptography on timing attacks, and a number of demonstrated exploits, both against specific ciphers, but also against more complex crypto systems like SSL. So there's a lot of background research in this area, but it's mostly in the area of cryptography. But what about your everyday web application? When does this stuff actually matter? So here's an example of a real live public website that's out on the internet right now. It's an insurance company, and they're health insurance. And if you already have a policy with them, then you can sign up for an online account. You have to enter your personal information, very sensitive stuff like your social security number, date of birth, and so on, in order to prove your identity before you can sign up for the account. Now, this particular website, I don't know if it's vulnerable at all. I'm not claiming it is. But this is the kind of form that I'm concerned about, and it's the kind of form I'd like to be able to test. Now, if this site returned differing error messages depending on which field you type in and got wrong, then clearly there would be an attack there, right? You could try to guess the social security number first, and then you could move on to the next field. And that stuff is something that pen testers typically search for. They look for those differing error messages, and they'll report on those. So that's a well-known issue. But if the amount of time the application requires to check each field varies, depending on what the data is, then there could still be a vulnerability here. And right now, I don't think most pen testers are looking for this. There's not good tools to check for this kind of thing. So this is my favorite quote from Yogi Berra. So in the past, there's been a lot of specific vulnerabilities identified in the area of timing vulnerabilities. And it's really interesting, but a lot of the techniques that are used are really basic, and they happen to work on that particular vulnerability, but they don't necessarily extend to other areas. And then there's been other research done that has tried to generalize timing attacks, but it seems like the research so far is still fairly immature. There's very few tools, off-the-shelf tools available. Last year, Meyer and Sandin presented a talk at Black Hat, and they released Time Trial, which is a really nice tool. It lets you identify if a timing difference exists in an application, both web applications and other applications. But it doesn't necessarily let you determine the actual risk of that, because You can't necessarily determine exactly the number of requests you need to perform the attack, and it doesn't give the pen tester quite enough tools to actually exploit the issue directly. And we also kind of felt that the statistical analysis could be improved in this area. It seems like a lot of previous researchers have used really basic statistics. For instance, in the case of Lucky 13, which is an exploit against SSL, they simply use the median to try to measure timing differences and really basic stuff from high school statistics. And so we thought this would be an easy area to improve on. Turned out to be a lot harder than we thought. So our goals: try to improve the statistical methods that are used to measure timing differences, and be able to answer the question for a pen tester in the time frame of a pen test: is this timing flaw actually exploitable? Can I actually tell my customer that, yes, this is something you need to fix right away, or this is really just something theoretical that would only be doable in 2 months' time? And then we also wanted to investigate the use of TCP timestamps, and if those timestamps could be used to help make these attacks more efficient. Previous researchers had kind of left this as an open question. So on to data collection, how we obtain the information we need to distinguish timing differences. First, a little bit about TCP timestamps. So TCP timestamps are a very simple mechanism to make TCP more efficient. What they do is whenever a host sends a packet as part of a TCP connection, the current time, the host's current time, is actually labeled on the packet. And so this could be really useful, right? Because now we can actually look at the time the host sent the packet rather than when we received it, and we can eliminate a lot of potential noise that occurs on the network. So it's really attractive to want to use this. And in order to get at TCP timestamps, you pretty much have to use a sniffer. You have to observe the packets directly because the TCP stacks don't expose this to the user space applications. It's also fairly tricky because the frequency of the clock for TCP timestamps varies from one operating system to another. So we have to be able to measure that clock frequency, and we worked out how to do that, but it's not trivial. And what this does is it forces us to actually analyze all of our data at a packet level and work out complex issues like if there's retransmissions of packets, if there's dropped packets, packets come out of order. We need to be able to address all those things in order to measure the round trip time of an HTTP request. And at the end of the day, after working with TCP timestamps for quite a while, we weren't able to use them directly to measure timing differences with any real accuracy. There's definitely information there, and we think by pairing that information with other timing data, we may be able to improve the results, but we don't have anything that sophisticated yet. But what this did is that it forced us down this path of doing packet analysis, of actually analyzing packets as they come and go from the network card, which actually ended up making our timing measurements much better by measuring the packets directly. And it makes sense because if you look at your typical very simple HTTP request, if you're trying to measure the time round trip times directly from user space, you're just opening a connection, sending the data, measuring the time you sent it, measuring the time when the data comes back into user space, then you're forced to measure the amount of time it takes for your data to be sent through the kernel onto the network card, the time it takes to do a TCP handshake, the time it takes for then the kernel to receive the response and then send it back to your user space application, and then the kernel eventually schedules your user space process back on the CPU. So there's all this extra time delay that's added to that, and that just introduces chance for more variance on your local machine. There's more variability because of different processes running, and so you'd think if you could simply measure from the time you saw the very first request packet that actually has data in it, not the handshake, we don't need that, and the very last packet that has data in it when we receive the response, then we could get a more accurate time measurement. So that's the theory, but does it actually work in practice? And that might be a little bit hard to see the histogram, but yes, it does work. Basically, you see here, we compared Time Trial, which is the tool released last year, and they have a very good user space implementation. It's implemented in C++. It's very, very fast, and they did a lot of work to try to minimize noise in user space. But just doing a much more naive request tool, but measuring the packets instead of doing it from user space, we get a much better distribution. So the blue distribution is our measurements of the same test scenario. You can see that the distribution is much spikier. It's a taller, a more narrow distribution. And clearly the time measurements, the raw measurements, are much smaller. They're much further to the left. And then looking at the median absolute deviation of these two distributions, which is a measure of variance, it turns out that the packet data was had 40% less variance. So it's clearly much better, so that's great. Another thing that we did differently than previous researchers is that we decided to do paired sampling, or to sample the data in tuples. So basically, if you have two test cases, for instance, one with a valid social security number and one with an invalid social security number, and you want to measure the time difference between the two, then those are your two test cases. Okay? We measure all those test cases one after another. We're very close in time, in wall clock time, and then we just repeat that process over and over. And in our terminology, one sample is actually a pair of those requests. Okay? So we collect the probes at about the same time. And the idea being that if there's any disturbances on the network or on the hosts during a period of time, then hopefully for a given sample, both of the requests will be affected in a similar way. Right? If for some reason packets start getting rerouted through a different router, if the remote host starts getting bogged down with other user requests, then any disturbances will equally affect both types of samples. And early during testing, we did one measurement, collected a bunch of samples on one host over the internet, and we got this distribution, which is awful, right? Basically, we have two separate distributions, one for each test case. But both of these test cases were completely separate. Like it was very multimodal. So some of the responses came back very, very quickly, and some took a very long time. And it's really ugly data set. And if you try to just apply basic statistics on this distribution as is, it's really difficult. Like, do you use the data on the left, or do you use the data on the right, or do you try to come up with some way to use both and combine them? But then when we looked at the data a little bit more closely, as a function of time of day, as when we sent the request, we saw this. And this is just a scatter plot. The red dots are the short test case, and the blue ones are the longer test case. And you can't really see the reds very much because the blue cover it. But basically what you see is that early in the test, all of the requests went really, really fast. And we got responses quickly. And then for some reason, something changed. And then all responses started to become very, very slow. And looking into it further, what I decided probably what happened is that Comcast has a feature called Speed Boost, or Power Boost, something like that. And what they do is they allow you to download files from a particular web server at unlimited speed at first. And then after a period of time, once they decided you've downloaded enough, then they throttle you back to your subscribed rate. So Comcast actually kind of screwed up our data set here because they let us go really, really fast at first, and then they throttled us back. So that creates problems, right? For if you're doing a pen test and this happens to you, what do you do? What part of the data do you rely on? Well, if instead of trying to treat these two data sets as separate, if instead we just take the pairwise differences between the round-trip time measurements for each pair, because they're paired, they were done about the same time, then you actually get the distribution at the bottom in the purple. So that's the difference in time between each pair of measurements. And so that automatically sort of normalizes it around a central tendency. And if you can measure then the location of that central tendency, meaning what is the average difference between the two requests, then you can decide, is this zero or non-zero? And if it's non-zero, then there's a timing difference, right? So that's one change in the way that we approach the problem. Jason's going to come up here and talk a little bit more about the statistical analysis. There you go.
So, thank you, Tim. So good morning. So now I'm going to talk a little bit, as he said, about the statistical analysis that we have done and the approach we have tried to take to analyzing these round-trip times and the differences in round-trip times. So recall what we're trying to do is uncover the amount of time one computation on a web server or another server takes versus a different types of computation. But if you've ever tried to deal with network data, even notwithstanding the Comcast Power Boost issue, you'll notice that network data are extremely noisy. So this is one of our best test cases. It's a sample of 500, or a series of 500 observations from this analysis we've done, or from a series that we have collected. And you'll notice it's quite clear what the problem is here in this series. You have 500 observations, and you have 4 of them that just went crazy. And basically, we have an average of about 100 millisecond round trip time on the vast majority of the cases, and then in 4 cases you have it go up to 400 or plus. So this is something we saw in all of the data. As I said, this was on a local network, a local VM, only 2 hops away, and you still get this type of these type of data. When you actually go over the internet to a web app that is further away, it gets much worse. So looking at the data on this data set anyway, it was about 1%, 1 to 2% of the time the data points were extreme in this way. Now when you, this is just one half of the pair. If you actually want to look at the other half, this is the all pairwise data here round trip times. If you take the differences, this is the type of data you're dealing with. And this is the thing that we wanted to deal with, and that does improve the analysis in the end, but it is still extremely difficult to use. So what these type of data, the problems they cause is that you can't use standard measures like t-tests or difference in mean tests. Medians we tested don't work out all that well. So what we wanted to do is come up with some way to filter the data and then use other more robust measures of central tendency in order to uncover the differences in round trip time in these pairwise data. So the tool that we went to first is something called a Kalman filter. And if any of you have ever done signal processing, it's a filter that is used in signal processing quite often. It does a great job under a wide variety of cases of smoothing things out. So for example, if we apply that the Kalman filter, the smoother, to that round trip time data, differences in round trip time data, this is what we get under one simple specification of the Kalman filter. So you can see here across those 500 samples that really the Kalman filter did smooth out those spikes, but it left them in because the idea is that those spikes have information in them. But we don't want to take them at face value. We want to control for the fact that they are so far, they're extreme outliers. So the next thing we wanted to try were a series of robust estimators. And we started with a box test, which Meyer and Sandin last year discussed here at Black Hat. Now, the box test is actually quite simple. If you take 2 distributions and you take 2 particular quantiles or spaces, so here I think it's the 6th and the 8th quantiles, 8% quantiles in each of these distributions. If these 2 boxes here, the blue and the pink boxes, if they do not overlap, which is the case in this plot, if they don't overlap, then you can say these distributions are different. So you can say, well, round trip times, the computation that these round trip times represent are different across these 2 test cases. However, if they do overlap, you say there's probably no real difference between them, between the two cases. So we, in preliminary tests, using the Kalman filter, not using the Kalman filter, we found that the box test under certain cases in our data, using the new data collection technique, didn't work that well in many cases. So we were looking for other things, and we turned to something called L estimators. And we went to L estimators for a couple reasons. The first is that they're extremely easy to understand, and second, they're very easy and quick to compute. Simply, what an L estimator is it's an estimator off of the quantiles. So here, I think these are the 25% quantiles above and below the median. And you take the values from those quantiles and then you average them. And that is your measure of central tendency. This can be extended. In this case, it's called the mid-hinge because it's the 25% quantiles, but you can generalize this to taking 4 points, or we also tried taking 7 points. And this one's a little bit different in the sense that we actually use the median in the calculation as well as those 3 points off to the right and left. So taking these new estimators and the Kalman filter, we needed to then figure out whether or not they were actually performing better than the box test, which ones perform better under certain circumstances, and whether or not the Kalman filter is actually going to help us analyze these type of data. So we performed a Monte Carlo analysis across 4 test scenarios. And here you can see that we have 2 local computers. One is a VM, one is a physical computer. And we have a VM, a remote VM, and a remote physical computer. And then we also have 2 different operating systems. What's important for the Monte Carlo analysis is that what we've done is we've taken 5 different deltas, so differences in the nanosecond differences. And then we've taken around 250,000 pairs of each test case. So there are 17 test cases in all. And what this led to is about 8.5 million different individual probes across all of these test cases. As I said, the objective here was to test all of these estimators and the Kalman filter systematically across a variety of cases. And this is a pretty standard Monte Carlo analysis, if any of you have ever done these in statistics. So for 13 different values between 50 and 100, or 50 and 10,000, those are the size of the series we take, because we really want to know how short or how few samples we can take and still get a good estimate. We're trying to make it practical. I don't do that. I do research usually, but Tim wants it practical. So we want to know how few data we can actually grab and come up with some kind of decent estimate of whether or not the round-trip times are actually different. So then, 480 times we repeat. We basically take a random sample, apply the Kalman filter, then we run the tests on the filtered data and the non-filtered data. For the L estimators, we actually did a bootstrap technique where we estimated on random samples of the filtered data and non-filtered data to come up with a distribution. And what all of this did is it came up with a distribution of errors for every single test case and every single parameterization across, I said this wasn't a practical part, right? Across all of these test cases. So there were a few billion different estimates that we took. So with this, then we get things that look kind of like this. On the 2, this is a level plot, or that's, I guess, what I call it. The 2 plots on the left and in the middle are they're the average errors. Each one of those squares is the average error within that parameterization of the box test. So in the left 2 plots, the red means the box test is doing really well. So you can see in the center where we've applied the Kalman filter, the box test does better across the broader range of parameterizations. Remember, going into any test that you're going to do, you don't actually know what the parameterization, what is going to be best for that data set in order to determine whether or not you have discovered a difference in round-trip times. And then, so that's on the left 2 plots. And then on the far right, you see the improvement in the Kalman filter, and mixed up the coloring here, but in the far right one, the gray is where the Kalman filter has done better, or the Kalman filtered data has done better than the raw data with the box test. So of course we also applied this to the other, the L estimators. This is the mid-summary. And the parameterization of the mid-summary is across the bottom, and the error rates are on the vertical axis. You can see across a broad range, the raw data in this case did much better than the Kalman filtered data with this estimator. We are actually able, with just 1,000 samples in this case, well below 10 or 5% error rate all the way through, about 0.3 in this case on the unfiltered data. The raw, or the filtered data, on the other hand, both one-dimensional and two-dimensional Kalman filter, did not perform very well. But this wasn't a consistent result. Actually, in a lot of cases, the Kalman filter did improve the estimates. Here it's about 7.5% on average. It smoothed out the results, and it made this estimator, the mid-summary, perform a little bit better. But unfortunately, this isn't good enough for an analysis, or to actually really determine. We're talking a 40% error rate here, still, even with the filtered data. So in summary, the statistical analysis, this is what we've gotten out of it. Just to say, we have 180 plots of the 182 of these plots for each one of these estimators, so I can't really go through all of them here. But on average, what we have found is the mid-summary in particular, and Tim's going to present some other results, performed better on average than the box test did over the data sets that we collected. The Kalman filter improves the hard cases. When we have very little data or very noisy data, the Kalman filter helps things a little bit, but not to the level that we had really hoped it would. The one caveat here is that this Kalman filter was not trained in any way. It was a parameterization that appeared to work pretty well in some test cases, and so we just stuck with it to estimate through. If you actually get down and train the Kalman filter, it might turn out to work a lot better than it has in our results so far. And then finally, one thing that we're wanting to look at for future is that we want to try out other filters and other weighting techniques. And one thing we're thinking about is using a clustering analysis to give particular weights to different pairwise differences in order to calculate the round time differences. So as I said, this is not the practical part. You don't want to do all of this for every analysis. So now I'm going to turn it back over to Tim. He's going to talk about how these results were integrated into the tool that he's developed in order to make this practical. Here, Tim. Thanks.
All right, thanks, Jason. So Jason did all of that work, really heavy brute force statistical analysis on a huge computing cluster, which is really nice. But now we need a tool that we can use day to day. So we created this little thing we're calling Nanone. The goal of it is to, first of all, identify timing differences in web applications, but then also to quantify the risk. You need to understand how many samples you need to collect to distinguish those timing differences. And that will tell you, as a pen tester or an attacker, how much time it's going to take to actually exploit something. And then also help out with the exploitation piece of it to create proof of concept. It's definitely a work in progress still, and it's not very user-friendly, so it might be a while before that is easier to use for the average pen tester. But this is the workflow for Nanone, just real briefly. At the beginning, you have to go through a templating stage where you need to sort of instruct the tool what your test cases are. If you have a valid social security number and an invalid one, or perhaps you have more than 2 of those test cases. And then you need to instruct it on what what the HTTP requests look like. Where does that data get embedded in the request? Is it in the post body or in the URL or what have you? And then from that point, the next 4 stages are pretty much automated. So you just run the collection scripts. It grabs a whole bunch of samples as a baseline, so you can actually learn things about the timing differences. Packet analysis is performed, which zeroes in on the actual packets you want to measure your round trip times between. And then you go through a training stage. So we came up with some training algorithms. Instead of trying to brute force every possible parameterization for our classifiers, we came up with algorithms that try to find the best parameters more quickly. They may not be perfect, but they seem to work pretty well. And then next, we actually test those parameterizations. So once we come up with a set of parameters for each classifier, we test them on a completely separate data set, a different portion of the collected data, which is really important to do. If you try to test over your training data, it doesn't work out well. And then at that point, at the end of the testing stage, you'll know how many samples you need to get a certain error rate. So will you need 1,000 samples to get 5% error, or do you need 100,000 samples to get that error? And then after that, if you want, you can also perform the attack. Just a little bit more about the training and testing process. Because our training algorithm may not be perfect, we actually train each classifier multiple times and come up with different parameterizations and then try them all out. One of the reasons for this is that if you train on different sample sizes, different numbers of observations, you actually get very different results in the training algorithms. If you don't give it enough data, then the training algorithms tend to not learn enough and they get bad parameters. If you give it too much data, they tend to overlearn. And this is a really common problem in machine learning, they tend to overtrain on the data, and then they work really well on the training set, but then it won't work well on the test set. So we try a bunch of different sizes, sample sizes, in order to tease out which ones work best. And then we try all of those parameterizations on the test data and find out which ones work best. And throughout this process, instead of just trying to find which classifier has the lowest error for a given sample size, what we're actually doing is sort of, it's not exactly a binary search, but similar to a binary search to identify what sample size is actually sufficient for a given classifier to perform the attack. And then whichever one has the lowest number of observations, that's the winner. So we kind of flip the problem around. So I also performed a Monte Carlo analysis against all of the same data that Jason did. This is a completely separate implementation, and we came up with the same overall results. For the most part, the mid-summary, quad-summary, or septa-summary classifiers do the best. Usually the mid-summary does a little bit better. In this table, what it's showing is in each cell, the number of observations needed to make a classification at 5% error. Okay, so lower is better. In some data sets, we didn't have enough data. We capped it at 20,000 observations because we don't feel above that is all that practical in most cases. And so in cases where the classifiers could not get down to 5% error, we just include the error rate, the best error rate that it achieved. So anyway, if you look through this, you can see that most of the time mid-summary was best. There is one case where the box test actually won, and we're not sure why. That was a consistent result. That data happened to be good for the box test. But in Nanone, it's trying all of these out and figuring out which one works best for you. So you're always working with the best classifier for your data set. All right, now time to do a little demo. Let's see, where did it go? All right, so we created a, let's see if that looks good. Okay. So we created a intentionally vulnerable application. It's designed to sort of mimic that registration site I showed earlier. And so you were supposed to know your own membership ID and your last four of your social security number. And if you enter those correctly, then you can sign up for an account. So this application has a timing difference in it. And you think, well, why is there a timing difference at all? You could just do a single SQL query to pull up and check both fields at once, and there would be no timing difference between the member ID and the social security field. But in this application, in this hypothetical scenario, the developer decided it'd be a good idea to encrypt the social security number field in the database as a field level encryption. So you can't really search for that value. So in this implementation, what happens is the member ID looks up the record, and then after the record is successfully found, then it decrypts that field. Of course, if there's no member ID that matches, then you don't have a field to decrypt. So that's where the timing difference comes in. What this is showing right now is just that demonstrating the different error messages you get depending on the different cases. If you enter a valid member ID and an invalid SSN, you get the same error as if you entered an invalid member ID. But once you get past that stage and put both fields correct, you get a different error message if you screw up the other fields. All right, so it's just going to register here. Okay. So we set up a script. In the script, it's not very easy to see, but we just need to instruct it on what the test cases are, a valid member ID and an invalid member ID. And then we also need to give it information about the HTTP request, what headers to send, where to embed that parameter in the request itself. And that's pretty much it. That's all the code that you'd need to write to get the collection script started. And here's running the tool to collect the data initially. There's a little bit of TCP timestamp information collected, but that isn't really isn't used at this point. And then it gives you, good estimates of how long it's going to take to finish your collection stage, which is really useful to estimate how long the attack will take later on. And then at the bottom, it gives you a little bit of debugging information about the way in which the packet analysis was performed, which packets were actually used to measure the round trip time. And then it also shows you what the delta was, what the estimated time difference between the test cases was. In this case, it's about 40 microseconds. And then from that point, you just take that database, SQLite database that has all the data, and you just run the training script over it. You can see here for each of the classifiers, it's running with a different number of observations on half of the data, the training data. And so it does a different number of observations throughout. And then it learns a different set of parameters for each of those runs, okay, based on the different numbers of observations. And then after all of those are done, it tries each of the different parameterizations against the test data. And a lot of these fail miserably on the test data. They just don't work. They were bad parameters. And the way that we zero in on the number of samples required is we start off with the number of samples that it was trained on initially, and then we just increase that quickly based on how bad the error is. And once we finally reach a number of observations that achieves less than 5% error, then we start to work our way back. We just kind of work our way back until the error gets above 5% again, and then we stop there and say, whichever one was best and underneath 5% is the winner for that particular set of parameters. And then later on, we compare all these parameters together for all the classifiers and their parameterizations. And at the bottom here, it gives you a summary of the results. So in this particular data set, against this intentionally vulnerable app, the quad summary classifier actually won. It only needed 231 observations to reliably classify. And then from this point, you know, based on the number of observations and how long it took to collect the data initially, you know how long it's going to take to perform the attack. One thing to keep in mind about these attacks is that even though it only takes 200 or so observations to distinguish the timing difference, you still need to brute force a whole bunch of values, right? You need to iterate over all SSN IDs or all member IDs. So, you know, that's multiplied by many thousand times. So very quickly you can get into the millions of observations required to perform the real attack. Here, the next attack script is running, and all it does is it tries to brute force or determine if a member ID is correct based on timing information. And then if it thinks the member ID is correct, then it tries to brute force the second field. And it doesn't need to do a timing attack in that case. So it just iterates over all of them. So jumping ahead to the end, this takes a while to run. It's not too bad. It's about 25 seconds for each failed attempt. Let's get to the right spot here. So looking over the results after a while, in this database, I set it up so that 1 in 10 member IDs is valid. And so it did find a few member IDs that was valid, and then it brute forced the SSN after that, and it was successful. But in some cases, you do get false positives. So down below, we have one member ID that it thought was valid, but after going through all social security numbers, it found that none were correct. So you have to write your code such that it can deal with those kinds of errors and either recheck it again or what have you. But it can still speed up an attack quite a bit. All right. Oops, got to get to the end of the slides now. Sorry. All right, so in conclusion, what we've managed to come up with is improved data collection through packet-based round-trip time estimation. And we've also come up with more resilient classification methods based on that better data. And then we've provided a tool that not only lets you detect timing differences in web applications, but also assess the risk and then exploit the issue. You might be wondering how you avoid these problems. Well, the easiest, most direct way to do that is to eliminate your timing differences. And that sounds easy. It seems like, well, if I just write my code so that it always takes the same amount of time, then it'll be good. But sometimes it's really tricky, like in the case of the decryption issue in the sample application there. What do? The data is encrypted in there, and I can't query for it. So it can be tricky. And another thing that people get caught with is when your code is compiled, a lot of times the compiler will reorder instructions, will take out code that is unnecessary, and that will actually introduce timing differences where you didn't think they exist. So I think it's actually really critical to be able to test. So if you're looking at an app you think there is a timing difference in, you change the code so there's not anymore, you need to test that because it could easily not behave the way you expect. If you are dealing with an application where the end user is involved, they actually have to interact with that interface, then an easy way to mitigate is to put a CAPTCHA on the page. With a CAPTCHA, you simply vastly reduce the number of requests an attacker can, the number of samples an attacker can obtain, so it's not really practically exploitable in that case. But a lot of times it's difficult to do. If you're dealing with an API between servers, there's no human involved, then now you have this issue that you can't use a CAPTCHA. So, all right, I think that's all we've got. So I think we can open up for questions. There are some mics down there if you want to use those.
No, this one. This one live? Okay, I don't think. Okay, there it goes. Did you guys? So you guys tested this with basically home network. Did you guys try this from a data center with reliable ping times to another data center that might have had?
We started with the 4 cases that we primarily tested for the statistical analysis. One was well, 2 of them were virtual machines, and 2 of them were physical machines. One was 2 of them were over the internet, and 2 of them were not. One of them was at Linode. It's a Linode VM. What was the other one? At your place, yeah. So a lot of the data was actually pretty noisy. I think you could do better with better pipes between your sites. And certainly previous researchers have talked about, look, you might have bad high latency or bad connection, but you can always rent a VM somewhere and get closer to the target in order to do the attack. And that's certainly possible, but we didn't do enough different situations to really compare that.
Sure. Thanks.
Last year at DEF CON there was a talk about an attack on memcompare on IoT devices over network. You're aware of that work? Or?
Yeah.
Yeah.
Definitely.
Okay. So because he had a lot of details about like how to get exact timing measures with network drivers and things like that. Mm-hmm. And do you have any practical, like real web applications that can be attacked with your tool, or just like the artificial one you created yourself?
So far, just the artificial. We really thought that we'd have something in place that we could go out and go find 0 days and the like. But honestly, the analysis, it was so much more effort than we thought it was going to be to get it where we're at that we just simply haven't had time to go after other applications yet.
I can certainly confirm that the analysis takes a long time, since the talk he was referencing was mine last year.
Okay.
Did you guys do anything to control the jitter of your attacking machine?
Yeah, we did. We did mostly the same stuff that Meyer and Sandin did with real time and then doing CPU affinity, which actually is really important because when your process switches from one core to another on your local machine, the real-time clocks are not in sync with each other, and that will, if it switches in the middle of the test, it screws it up.
Did you turn off power saving as well?
Turn off what?
Power saving. That made the biggest difference for me.
Really?
Yeah.
I don't. Yeah, I didn't. I doubt my machine was going into power saving mode at all because it was really slow and cranking, and the fan was going crazy. But maybe.
Yeah, I found it made a big difference. The other question was, when you were running the Monte Carlo subsets, were you using sequential lengths or were you using random samples?
Sequential series, you mean? Like as the sub? Yeah, they were sequential.
Okay.
Yep.
Yes. The Kalman filter assumes you have a time series, right? So and so we just kept with this, estimated the Kalman filter on a series of data and then used that. And then we just picked random samples from the 250,000 pairs we had for each test case.
Okay, so you didn't use sequential samples for the Monte Carlo?
Random subsequences.
Yes, random sequential samples.
Okay.
Yeah.
Good questions. Any more?
No, I'll come talk to you.
Okay, that sounds good. All right, I think that's it. Thank you very much.